Welcome to the 12th National Competition Finals. It's my pleasure to welcome you here. I'm Diane Sukamaki from the College Board. I think probably I've met most of you throughout the weekend, but there might be a couple new people here. This is a beautiful facility, isn't it? And we're so honored to be here at George Washington University. I'd just like to remind everyone, please turn off your cell phones, your Blackberries, your anything that beeps. We want to make sure that the students are not disturbed. No photographs or videos during the presentation. If the students figured out how to use those really cool video cameras last night, you can't use those while you're here. And please, no coaching from the audience. We're going to have the presentation as we described at dinner last night. For those of you that were at dinner, the judges will leave after the students present. The presentations are 12 minutes. The doors are now secured, so no one else will enter the auditorium or be able to leave the auditorium until the students are finished presenting. When the students return from their Q&A, the judges will follow in about 3 to 4 minutes, so please be seated, and we will then come in and begin the next presentation. It's my privilege this morning to introduce again a good friend of the Siemens Competition, Dr. Thomas Jones. This is his second year as our lead judge, and we were thrilled that he could come back and be a lead judge with us again. He is a veteran NASA astronaut, a scientist, a speaker, and an author. Tom was born in Baltimore, Maryland, so he's local to the area. He's a distinguished graduate of the U.S. Air Force Academy. He served on active duty in the Air Force as an officer for 6 years. As a pilot and aircraft commander, he led a combat crew of 6, accumulating over 2,000 hours of jet experience. He left the Air Force to pursue his PhD in planetary sciences at the University of Arizona in Tucson. His research interests included the remote sensing of asteroids, meteorite, spectroscopy, and applications of space resources. He worked at the CIA's Office of Development and Engineering before joining Science Applications International Corporation in Washington, D.C. as a senior scientist. Dr. Jones performed advanced program planning for NASA's Solar System Exploration Division, investigating future robotic missions to Mars, asteroids, and the outer solar system. After a year of training following his selection by NASA in January 1990, Dr. Jones became an astronaut in July 1991. He flew on successful flights of Space Shuttle Endeavour and on Columbia and Atlantis. In February 2001, Dr. Jones and his crew delivered the U.S. Destiny laboratory module to the space station, and he helped install the lab in a series of 3 spacewalks lasting over 19 hours. The successful addition of Destiny gave the first expedition crew the largest space outpost in history and marked the start of onboard scientific research at the International Space Station. A veteran of 4 space flights, Dr. Jones has logged over 52 days. That's 1,272 hours in space. I'm sure we all envy that experience. Currently, he is a renowned author, scientist, speaker, consultant, and active in the debate over our nation's space exploration policy. His awards include the NASA Distinguished Service Medal, 4 NASA Spaceflight Medals, the NASA Exceptional Service Award, the NASA Outstanding Leadership Medal, Phi Beta Kappa, and the Air Force Commendation Medal. It's truly an honor and privilege, Tom, to have you here as our lead national judge. Please join me in welcoming Dr. Jones.
Well, it's truly an honor for me to be with you this morning and to serve as the national judge for the Siemens National Science Competition. I'm joined this morning by a really distinguished panel of judges who have donated their time and their attention and dedication and interest to evaluating the science presentations that we'll be hearing this morning. I'm really glad to be with them all. They are truly an outstanding panel, and I'm sure that our students will find their questions both engaging, interesting, and provocative. So let me introduce our panel. I'd like each of the judges, as I call your name, to just stand and turn to the audience and say hello to them this morning. So we have a panel of a dozen judges joining me. First, Eric Weisstein, who's a senior researcher at Wolfram Research Incorporated. Eric. Next, Mona Singh. Mona Singh is an associate professor of computer science at Princeton University. Kevin Sill is chief science officer for Intazyne Technologies. Vladimir Retak is a professor of mathematics at Rutgers University. Jay Regan, associate professor of environmental engineering at Penn State. Antonio Montalban, who's assistant professor of mathematics at the University of Chicago. Gert Lankriet is head of the Computer Audition Laboratory, Department of Electrical and Computer Engineering at the University of California in San Diego. Gert. And next we have Maria Jiha, who is assistant professor of astronomy at Yale University. Tejal Desai is next, and she's professor of bioengineering and therapeutic sciences at the University of California in San Francisco. Where's Maria Chodnovsky? Maria is joining us as an associate professor, Department of Industrial Engineering and Operations Research, Department of Math at Columbia University. I see Kim Boyer down there on the right side of me, and he's professor and head of the Department of Electrical and Computer and Systems Engineering at Rensselaer Polytechnic. Victor Ambrose, right here in front, is Silverman Professor of Natural Science, Department of Molecular Medicine, University of Massachusetts Medical School. Thank you, Victor, and thanks to all the judges. They've put in a lot of work ahead of time, looking over the presentations and submittals by the students. We're very interested in what you all have to say and what we're going to learn with you this morning and the rest of the day. So we look forward eagerly to your presentations. And without any further ado, let's have the first team come up. We're going to do our team presentations this morning. First team is Akash Krishnan and Matt Fernandez from Oregon Episcopal School in Portland, Oregon, and they're going to be telling us about the recognition of human emotion in speech. And I think the big emotion right now is anticipation. So, Matt and Akash, come on up.
Good morning, everyone. I'm Matt Fernandez.
And I'm Akash Krishnan. Before we start the presentation, we would like to thank the Siemens Foundation, the College Board, and George Washington University for giving us this opportunity to present our research here today. At the core of emotion recognition, there exists the human speech component. Speech is produced when the lungs contract to expel air, which is forced up through the bronchial tract and into the trachea. This sets the vocal cords to vibrate and produces sound at different frequencies that exits the body through the mouth or the nasal cavity. In order to analyze speech, it needs to be converted into a digital format, which can be done through analog to digital conversion. There are two representations of digital audio signals. The first is the time domain, also known as the waveform, which is plotted down below here, which is a series of amplitudes over a period of time at a constant sampling rate. The second is the frequency domain, which is a histogram that is composed of the number of occurrences of frequencies, and in the example below, the most dominant frequency is 120 Hertz. Speech signals are composed of words, silence regions, background noise, and tone. Variations in these signals occur based on age, gender, culture, and the emotional state of the speaker, and because these variations exist, it allows one to classify and recognize those factors by extracting relevant information and then processing it. One key thing to note is that humans are relatively good at recognizing these factors, but it's very difficult for computers to do so because all they have is just a bunch of numbers.
So from these digital speech signals, we can extract important information called features. we extract 18 functional features, which are composed of both energy and frequency-related information. In addition, we extract 13 metal-frequency cepstral coefficients, or MFCCs, and their first and second derivative plots for a total of 57 features. Emotion recognition is the ability for a computer to recognize emotion through relevant data processing. This is a new and quickly growing field in the broader area of digital signal processing. Some of the broad applications for our research and emotion recognition in general involve human-computer interaction with a voice component, so improving call centers, robotics, gaming are all places where our research can be applied. Our objective and goal was to create a highly accurate emotion recognition system, and the overall goal for the field is to create emotion recognition systems that can achieve results similar to that of a human. In addition, we attempt the real-time recognition of emotion, something few researchers consider but is essential for many applications. The Interspeech 2009 conference, held in Brighton, UK, had an emotion challenge designed for it about a year in advance by Bjorn Schuler and 2 other German researchers. These researchers created a baseline system for which the methodology and results are published. This allows us to directly compare our methods and our results to this baseline system on the same training and testing set from the FAU IBO Emotion database. This is one of 3 databases that we use in our research and is the one shown in red on this chart. This data comes from children interacting with a pet robot dog, which the dog then elicits emotional responses in the child. There are 3 central tasks to emotion recognition. The first step is pre-processing, where we convert the signal from analog to digital and filter out irrelevant data. The second step is feature extraction, where we extract things like the fundamental frequency or metal-frequency cepstral coefficients. Finally, we use this feature data to train our system to classify new information. We'll now discuss some of the key differences between our methods and the baseline system's methods and why our system offers improvements. For the pre-processing step, the baseline system uses a simple noise reduction method. However, we additionally fully remove all silence from the signal, including silence in between words. So if you look at the top plot there of the original signal, that is what the baseline system uses. However, we chunk out the parts in red, which are silence regions. This is because those regions do not contain any acoustical information. And because we use exclusively acoustic features, it doesn't make sense to use that data. And in fact, using it decreases one's results.
The Interspeech 2009 baseline system extracts a total of 384 features, which is composed of functionals that are calculated at the global level. For our improved system, we actually only need to extract a total of 57 features to receive the same base performance. And we are able to calculate the functionals at the frame level. This allows for a better precision in our feature modeling. In addition, the baseline system uses a synthetic minority oversampling technique and normalization and standardization methods to increase performance and decrease computation time. However, this is only specific for the baseline's classification algorithm and not for ours, so we don't need to use them. For our improved system, we also sort our MFCC data from least to greatest, which we'll talk about in a couple of slides and how it affects our performance. And we also use foul relative features to account for speaker variations and make our features speaker independent. Before any feature extraction occurs, we segment our audio signal into frames of 25 milliseconds in length. These would be frames 0, 2, 4, and 6. From each of these frame boundaries, we shift them in the time domain by 10 milliseconds to the right to account for changes that occur between 2 frames. And this is called overlapping frames, and these are frames 1, 3, and 5. From each of these frames, we extract a total of 57 features, which are composed of functionals, the minimum, mean, and maximum. And we calculate the average for the entire file for each of these features and eventually the entire emotion, so that after the entire training process, we have a unique set of 57 features that define each emotion. We also post-process our MFCC data. The plot at the top here represents an entire signal's worth of MFCC features. And what we do with this data is we sort it from least to greatest. So the smallest values on the left side and the greatest values on the right side. This is an important step we do in recognizing emotion, and it's a novel step we actually do. And we'll talk about how that works in our classification engine and how it affects our results. The last task is the classification task, which involves, for the baseline system, a sequential minimal optimization algorithm, which is an efficient multi-class machine learning algorithm. However, it can only classify once per entire file, and it takes a long time to train compared to our system. Our improved system uses a simple, which is tremendously faster, rule-based voting system, which is able to classify over 39,000 times per an entire file. And this is due to frame-level classification. So right now, frame level classification and feature extraction is very important. In addition, we increase performance even further by implementing a feature optimization, but we unfortunately do not have enough time to talk about that in this presentation. To classify the first 18 features, or the functional features, we calculate the averages and the ranges for each of the emotions we have, and for each of the features we have, and in this case, this is the plot of the first feature we have. We then devise emotion groups based on the overlapping of error bars. So one emotion group consists of the emotions anxiety, happiness, and anger. During classification, we try to figure out which emotion group the feature we're trying to classify falls under. And whichever emotion group that is, we give each one of those emotions a vote. We do this for each of the frames we have and for each of the features we have. So after the entire part 1 of the training classification process, we have a unique distribution of votes to each emotion. This is also coupled with part 2 of the classification, which involves the MSCCs. The plot at the top represents the average of the first coefficient of MSCCs among the other 39 for each of the emotions we have. And then we determine the variance graph based on the dissimilarity of emotions at each given sample. As you can see, at the top left here, there's a high importance because the emotions are very diverse. They're very spread apart, and it's easier to classify. So we give it more importance during classification. Whereas in the center region here, the emotion values are all clumped up together, and it's hard to differentiate from one from another. So what we do is we give less importance to the classification process. During classification, we try to figure out which emotions model is closest to the one we're trying to classify using square distance at each given sample, and whichever emotion that is, we give that emotion a vote based on the variance at that given sample. So this incorporates the importance levels, and we do this for each of the 1,000 samples we have and for each of the 39 coefficients we have. So after the entire training process, we have whichever emotion has the greatest number of votes is the one we classify using our system.
We'll now discuss how our results differ from the baseline system and what parts of our system specifically impact our results. So on the left side of this chart is the best baseline performance at roughly 40.9% for the defined training and testing set of the contest. As we move from left to right, we'll add in chunks of our system and see how it affects the results. Using our classifier, the results actually drop dramatically to 27.6%, only slightly better than chance prediction. This is because our classifier is specifically designed for frame-level functionals, MFCC resorting, and file relative features. So when we add back in those steps, the results increase to 46%, better than both the baseline system and the winner of the contest. So by additionally using our speech isolation and feature optimization steps, the results jump even further to almost 50% relative, better than the baseline system for performance on the same training and testing set. In this chart, we see in blue the InterSpeech 2009 baseline's performance, and in red our improved system's performance. On the right side is the unweighted average recall, which was shown on the previous slide. Additionally, each of the pairs of columns represents each of the emotion classes in the contest. Our system outperforms the baseline by more than 10 percentage points for each of the emotion classes, showing that it works regardless of the emotion, not just on a select few. In conclusion, we've accomplished our objective. Our system is state-of-the-art and is achieving results 15 percentage points better than the leaders of the field that won the contest, and almost 20% better than the baseline for the system, for the contest. In addition, we have created a workable real-time emotion recognition system, something that we have demonstrated to some researchers, and they've been very impressed, but we unfortunately do not have time to present here today. We filed for a provisional patent on our methods and are working to file a regular application in the next month. Additionally, we've been contacted by the US military and are starting to work with them to start using some of our algorithms for military intelligence. In summary, our major contributions to the emotion recognition field involve increased emotion recognition accuracy, faster classification algorithms, and our novel MFCC resorting method, which could have broader implications than just what we've explored in this project. Some of the applications that we're especially focused on for this project is creating a wristwatch-like device for autistic children. Autistic children can often have difficulty recognizing the emotions that are being spoken around them, and this can lead to them having a very difficult time interacting, especially in peer-to-peer scenarios. So we propose creating a wristwatch that would use faces or colors to display emotions to children and help them interact better in society. Also, to extend our project, we're working to use speech recognition to classify in addition to how the words are spoken, which is what our current system does, to analyze what words are spoken, because that, of course, additionally affects emotion.
Lastly, we would like to thank Dr. Steve Decker, Dr. Bevan Daglin, Dr. Jan Santen, and Dr. Björn Schiller. These are our references that we have cited in our presentation today.
Thank you very much for listening. We appreciate your time.